This is stuff that largely you already know. It's very, very minor extensions of stuff you already know. Okay, so let's go back and let's look at, first of all, let's look at square roots very, very briefly. And you know those well. If I ask you what is the square root of 81, your answer to me is what?
9.
It's 9. Good. It's 9 because.
Plus or minus.
Okay. Is it plus or minus or not?
No.
Okay. It's an excellent question. No, it's and this is something. I think this is honestly a topic that a lot of. I mean, if you look at a lot of the Algebra 2 textbooks, I think they make this very confusing because a lot of books, ours included, erroneously say that the square root of 81 is plus or minus 9. It's not. The square root, the principal square root of 81 is 9. That period. Okay. Why do the reason people might say that it's plus or minus 9 is because when we solve an equation by square rooting both sides, we get a plus or minus. And we'll look at that in just a second. But it's a great question. If you hadn't asked it, I would have brought it up anyway. Okay. But before we get there, I want you to tell me, why is it that the square root of 81 is 9? Because 9
times itself.
Okay, because 9 squared is 81, right? Okay, so the reason that is true is because of that other statement, right? Because 9 squared is 81, okay? Now, let's extend that a little bit. The cube root of 27 is what?
3.
Is 3 because
3. 3 to the third.
Okay, listen please. Because 3, I gotta pick a different number here. Hang on. I know this. You know this stuff. It's not hard, but that was a bad choice on my part. Let me instead ask you for the cube root of 8.
2.
That's 2. Okay, please stop talking. Because 2 cubed is 8. Okay. What about, we'll do one more of these. The fourth root of 81 is 3. Because that's a 3. Because
3 times 3 times 3 times 3.
okay, in other words, 3 to the 4th is 81. Okay, you can see a pattern here. Now, keep in mind that when we write a square root, we're being lazy. That a square root is really a second root. And a cube root is really a third root, right? Where's the 2? We're just lazy. It's right there. There is an invisible 2 that we just choose not to write because square roots are so common that we don't want to get writer's cramp, I guess. But it's there. There is a number 2 that sits on the square root, okay? So tell me this then. The nth root of A equals B when what is true? Very good. Okay, that is in general true. Okay, good. And so this is a general way of talking about a radical. That number that sits on the radical sign is what we call the index of the radical. So if the index is 2, it's a square root. If the index is 3, it's a cube root, etc. Okay? All right, so let's explore this a little bit further. What is so the square root of 4 is 2. The square root of -4 is
2i.
Okay, it's 2i, isn't it?
Yes.
It's non-real.
Yep.
Now, for the moment, and in fact, we're not really going to worry about imaginary numbers too much from here on out. We've dealt with imaginary numbers. You'll go much further with that in college. But just like we did in Chapter 6, a lot of the time from here on out, at least in what we're going to do for the rest of the year, we're going to sort of focus on real solutions. Because a lot of times in real life, that's what we do. We look for real solutions. And so the questions are typically going to say things like they do in Chapter 6. list all real solutions, set for multiple solutions exist, separate them with commas. If no real solutions exist, enter
N.
n. Yeah, n for no reals. Okay, so this would be a case where we would get a big fat n, whoops. Because there are, what's that? What, would you like those? Okay, there are no reals there, and what's the obvious red flag?
Negative.
Okay, the negative sign inside the radical. Okay, now let's compare that to the cube root of 27.
3.
Okay, it's 3, isn't it? Okay. What is the cube root of negative 27?
Negative 3.
What is it?
Negative 3.
It's negative 3.
Oh yeah,
Okay, there is a key difference there. Cameron, quiet. There is a key difference there. The difference is that it's a cube root compared to a square root. Now we want to see if we can make some big generalization from those two small examples. This is an example of empirical reasoning. This is inductive reasoning, not deductive reasoning. You gotta be careful with it, but I will carefully guide you so you don't make any wrong conclusions with this. How about it? The answer is negative 3. Okay, and here's why. Because negative 3 cubed is negative 27, right? Exactly.
Oh, that makes sense. So if it's anything to an odd number, it would be a
Bingo.
real number.
Bingo. Okay, so there is the generalization we can make. We can take an odd root of any negative number, and it's fine. We get a negative answer. But we can't take an odd root, or excuse me, we can't take an even root of a negative number because this is not true, is it? We don't get negative 2, right? Because negative 2 squared is not negative 4, right? We don't get positive 2 because positive 2 squared is not negative 4. There is no real number, we know that, right? We have to include an I, that's going to give us a negative answer back when we square it. Because we know, and we've known this for a while, that a negative number to any even power is always
Positive.
positive. It's always positive, isn't it, right? Okay, but a negative number to an odd power is negative. Okay, so we can make that generalization then. We know that if n is odd, sure, we can take a root of a negative number, but if it's even, we cannot. Okay? All right, I'm going to go back to Terrence's question earlier now. Why is it that the square root of 9 only equals 3, not plus or minus 3? But if we solve the equation x squared equals 9, we all know we're getting what answers? X equals plus or minus 3. Okay? Now we can see clearly that those two solutions both work. We can plug them in and check them, right? And they both work. Negative 3 squared is 9 and 3 squared is 9. Where do they come from though? They don't come from the square root process. You might remember the missing step, the secret missing hidden step that we talked about earlier, but we've never used it since, and we still won't. So it probably didn't make a huge impression on you, but hopefully this will ring a bell. If I square root both sides, what do I get? Well, on the right side, what do I get?
3.
3. I get 3. The answer is 3. But on the left side,
Plus or minus.
no, okay, it's the left side was a little weird. Let's think of the left side for a second. Let's just define that as some function. We'll call it f of x. So if f of x is defined as the square root of x squared, let's just do a little bit more carefully guided empirical reasoning here. So if we try a couple points, let's try negative 3. What is f of negative 3? If f of x is this weird square root of x squared deal. If I plug negative 3 in, what is that function going to spit back for an answer?
3.
It's going to spit back 3, isn't it? Because negative 3 squared is 9, the square root of 9 is 3. What if I plug in a positive 3? What's it going to spit back?
3.
Okay, now what function do you know that leaves positive input values alone and changes negative input values to positive?
Absolute value.
Absolute value, exactly. So what this function really is is an absolute value of x. And so what we're really doing is solving the absolute value equation. Absolute value of x equals 3. What are the solutions of that equation? Plus or minus 3. Okay? So that's where that plus or minus comes from. It's not the square root. Okay?
So when you're solving for something like, what's the square root of that number, it's asking for the absolute value.
Well, okay, if remember what our rule was. If we take a square root of both sides, we had to include the plus or minus.
Okay.
Now, we're going to generalize this, though. Sometimes we'll have to do that, and sometimes we won't. And it's not, I mean, we'll see if we can make that connection here. We always skip over, we don't show those steps algebraically, but we recognize that they're there. We know instead, and we've drilled this in, everybody's really good at this, we know that if we take a square root of both sides of an equation, you all know to include a plus or minus before your answer, right? Okay, now let's compare that to something like this. What if we're solving the equation x cubed equals 8? Okay, what do I do in this case? I cube root both sides, okay? So if I cube root both sides, what's the cube root of 8?
2.
What's the cube root of x cubed? It's just x. It's just x. Let's explore, let's compare that to, let's call that g of x. That's a new function. We'll compare to f of x. If g of x equals the cube root of x cubed, what is g of 2? 2. Sure. It's 2, isn't it? Okay. What is g of negative 2? Negative 2. Okay, that's not an absolute value function, is it?
No.
That's, in fact, what is that function? If I put an input value in and it's always the same as the output value, g of x just equals what? Do you know? No. X. That's it. The cube root of x cubed is just x. So we get the answer x equals 2. One answer, one solution. Okay, what do you hypothesize is going to happen here if I don't even need the exact answer. Well, you can give it to me. What's going to be the exact answer to this one? If I take the 6th root, hang on, not that, sorry. What if I do x to the 6th equals 64?
Just the square root to the 6.
It's plus or minus 2. Good, it's plus or minus the 6th root of 64. And we'll talk about how to take 6th roots in a second. I'll show you on your calculator, there's some shortcuts. But the 6th root of 64, that's one that you're going to get familiar with. That's just 64 because, or it's 2, sorry, it's 2. Because,
like, how's it 64?
yeah, sorry. Because 2 to the 6th is 64, okay?
Wait, why is it plus and minus on
Okay,
that one?
why, well, how come? You guys tell me, how come?
It's an even exponent.
Exactly, because
So
it's
even
even.
if it was like to the 4th, it'd be
Yep,
plus
it
or
would still be,
minus.
it still would be.
Just odd powers aren't.
Very good. That's the connection. The 6th, the fact that we started off with an x to the 6th is what necessitates that plus or minus because it's even. Okay, yes?
So what will the assignments be like on there?
Really simple. You're going to be doing things
Like this
like,
simple?
here's an example of,
Or easier, please?
well, when we get to some problems, these are actually the hardest problems out there, would be ones like this. The easiest ones are even, you'll see, first assignment is very simple.
And did you already have it on?
But it's one I want you to do it, you gotta do some practice to ingrain that in there, yeah.
Do you have it on there? Or?
No, it's not quite, almost,
Okay.
not quite. Okay. So what about this then? What if we had x cubed equals negative 64? What's x equal to? What's the solution or solutions there?
That would be
Negative 4. Okay, and the reason it's negative 4 is because negative 4 cubed is negative 64.
Well, it
right?
has to be negative if the answer's negative.
Correct. Yeah. For an odd root, you can always make that connection. Yeah. Good. Okay, so the moral of the story: odd roots. If I take an odd root of both sides of an equation, one solution. If I take an even root of both sides of an equation, plus or minus. Okay?
Oh, that's so you don't really have to do the math, you just try to figure it out.
Right. Right, exactly, yeah. Now, what this allows us to do, this is like, if you could, I'm not kidding, this is the hardest question you would possibly see on this assignment. I'll give it to you right now. And this, you'll see that it's not that big a deal.
It can never be just positive.
Okay, so what if we had something like this? What if we had 3 times the quantity x minus 1 to the 4th equals, oh, I'll even make it harder. That's not hard enough. Minus 2 equals,
How does minus 2 make it way harder?
well, it doesn't. You'll see this won't be that hard.
Equals 1.
Okay, here's the point of my story. It's the hardest one we could possibly do. Now, the whole point of us talking about this is, how are we going to solve this equation? Now, up until now, what we would have had to have done with this, by the way, is we would have had to have expanded this whole thing out and gotten a 4th degree polynomial that we solved. But remember in chapter 5, we had kind of 2 categories of quadratic equations that we solved, easy and hard. The easy ones were ones where we could point to a single x and isolate it by reversing order of operations, right? Like that. The harder ones were the ones where we had mixed x squared terms and x terms. And so we couldn't point to a single x, and so we had to put it in standard form and solve it. You know, initially we solved them all by factoring. Eventually, that quadratic formula helped out quite a bit, right? But that's the harder kind. This is a kind that we're going to make the extension now. The whole point of this is we can take the hard stuff we did in chapter 6, and we can oftentimes make it much easier in the case where we can point to a single variable, right? The reversing order of operations works just like it did before, but now we're filling in that blank. We didn't really know how to deal with the exponent part of reversing order of operations until this, right? So I can point to a single x right there. So if I reverse order of operations, where does that take me?
Plus 2.
Yeah, the first step is going to be add or subtract to both sides, right? So we add 2 to both sides. So we end up with, after that step, we get 3 times x minus 1 to the 4th, okay, equals 48. I don't know if I made this work. Yeah, I did. It works. Okay. So now what's next?
Divide by 3.
Divide by 3. Okay, so multiply, divide by 3. So we get the quantity x minus 1 to the 4th equals 16. Okay, now here's where we would have been stuck in the past, right, before today. Because now we get up to exponents, and the exponent isn't a 2, it's a 4. But now we know what to do. What do we do to both sides of an equation in this case? Okay, we're going to take a 4th root of both sides. That's an even root, right? And so I have to include, good, I have to include a plus or minus, what in this case? What's 4th root of 16? 2. Good. Okay, and so then last step, add 1. Yeah, we're going to get 2, aren't we? We're going to get x equals 1 plus or minus 2. If we take the plus, the solution that's given to us by the positive sign, what do we get? 3. If we take the other solution, we get, very good. How would we check that on a test?
Plug it back in.
Plug them in. Plug them in. Absolutely.
And that's as hard as it gets.
That's as hard as that assignment's going to get.
I like that.
Yeah. Okay. No big deal. All right. So, okay. So next issue. Now, this is really just some vocabulary and terminology, but it's important. It's gonna later on. This is going to be very, very helpful. So even though it's not difficult, it's still very important. Okay. What I want to do now is let's explore how we could write. Let's take something general like the nth root of a, and the question is, how could we write that as a power? In other words, what's the exponent going to look like? Okay.
A to the A.
Well, let's look. Let's take a simple example. Let's take, how about just a square root? So if we've got a square root function, I know that the square root of a to what power equals a. In other words, let me write it a different way. In other words, would you agree that the square root of a times the square root of a equals a?
Yes.
Yeah.
Does that make sense? Okay.
Oh, yes.
Okay, so, everybody agree? Okay, so if I write then, what I want to do is, and this is kind of this is a minor league proof, but we don't do very many proofs in here, just because we don't have time. I want you to at least see how some of these things work. If I want to find out what the exponent would have to be associated with the square root, let's just call it k. Let's just call it k. So I'm going to call this something like a to the k times a to the k equals a to the what?
No, A.
Just plain old a is to what power? 1, sure. Okay. Okay, good. No, that's right. So, focus. Focus, focus. I want to see everybody's attention up here for a second, okay? Now, we know properties of exponents inside now. If I multiply like bases, a to the k times a to the k, what's the result?
A to the K plus K.
Good, which is a to the 2k, right? Okay, make sense?
Yes.
Okay,
Because you add exponents.
good. Okay, that's equal to a to the 1. Now, I want you to think about this for a second. When we get to chapter 8, we're going to learn some techniques for solving for unknowns in the exponents. Okay, but for now, we don't need anything fancy like that. If I know that a to the 2k equals a to the 1, so the bases are equal, for this equation to be true, what relationship has to exist? Okay. No. No. What about this? What if I have a to the m equals a to the n? What's the relationship between m and n?
They have to be equal.
They have to be equal, don't they? Doesn't that make sense? If the left expression equals the right expression and the bases are the same, the exponents have to be the same also, right? Okay, so what this tells us, by making that connection, we're able to distill this down to a much easier equation. We can just, because the bases are equal, we can just equate the exponents and we get 2k equals 1. So what's k equal to?
2.
1
1, 2.
1/2. Yeah, right? If I divide both, can you, that k, somehow that k got kind of, let's do that again. If 2k equals 1, then k must equal 1/2. Okay? Now we could do another example like this to maybe try the same thing for a cube root. But I bet you can make this extension. The index of the radical for a square root is a 2, isn't it? Right? So we just said that the square root of a, aka the second root of a,
A to the half.
right?
Really?
Yeah, that's it. That's what we just said, right? We just proved that the square root, aka the second root of a, is equal to 1, a to the 1 over 2 power. So I want you to tell me then, in general, the nth root of a is equal to what?
A 1 over 2.
A 1
A
over
1 over
n.
n.
A to the 1 over n.
Oh, because it's so whenever it's in the little square root above it,
Yes.
that always goes below and you just put a 1 above it.
Yes. Okay, so that's hugely important, right? So these are equivalent notations. They mean the same thing. Listen, please, we got too much talking. If we want to ever write a radical as a power, which we often really want to do, powers are much easier to work with than radicals because powers, we know the rules and properties of exponents so well, right? We know those, we can use them. The only difference is, in this case, well, the numbers instead of being integers would just be fractions. Big deal, right? Yes, sir.
Can we do, like, after all this, can we do an equation of or the square root of n, or the blue one?
Blue one, okay.
Can we do it?
Yeah, absolutely. Well, let's do one right now.
So does k always equal 1/2, or?
Well, no, we just solved for it in that one case. The important thing is that this is always true. We know that the nth root of something, of some base, call it a, is always equal to the base to the 1 over n power. Okay? So I want you to tell me then, if I want to take the 13th root of 57, how could I write that as power?
57.
That's it. Okay? That's useful. Because if I want to, it's sort of useful right now, but it's going to be really useful very soon. If I want to, for example, approximate a radical with a calculator, this gives us a really easy way to do it. Now, on your graphing calculators, there actually is a way that you can approximate a root by actually making the graphing calculator make it look like a 13th root. But it's not, it's sort of, it's too much trouble. It's really not worth it. What you have to do is this. If I want to,
You got a new calculator.
I did. So, I'll stand over here. So if I want to make the calculator actually create an expression that looks like that, what you have to do, I'll just show you, but don't ever do it this way. You type in the index first, which is 13, right? Type in the index, and then you go to the math menu, and you choose the 5th option, and look what it does. It puts the 13 in the index.
Wait, how is that too much work?
Well, it's not right now, but eventually it will be. You'll even today you'll start to say, okay, really this other way better. I promise you.
Okay.
So if we put in then a 57 inside, it gives us that answer. But this is better. What we can do instead is just take the base 57 to what power?
113.
Yeah, the 113.
Wait, don't you still click as much?
Okay, you do for this one, but wait till you see the next one. Okay.
No.
Same answer, right? Okay, perfect. All right, so.
You can also make a fraction.
And so, by the way, you want to know what kind of problems are on the assignment. Some of the problems are going to be things like write this like this, or write this like this. Right? Okay.
Let's keep all of it like that.
Oh,
I need
no.
to get like
Are we
easy
gonna have to
points
simplify
here.
it?
Okay, so now what about this? Okay, what do you suppose? What do you suppose this means then? What if we have something like, let's say, x to the 2/3?
Flip it.
Okay, now look at the difference here. Okay, so, no, you can't just flip it. But look at the difference between this and what we just said. We just said that an nth root is always equal to an exponent 1 over n, right?
Yeah.
So what if we've got x to the 2/3 power? Now, could you use, here's my question, could you use your properties of exponents to write this as a product of exponents that might make sense? So could I write it like this? Could I write this as x to the something to the something?
No.
And take advantage of what we just learned.
Yeah.
X to the 30 squared.
X to the 1/3 squared. Would make sense, wouldn't it? Now think about why that makes sense.
How does that make it easier?
Well, I'll show you. I'll show you. You'll see why here in just a second. So this is a good idea because we know how to interpret x to the 1/3. What is that?
Cube root.
That's a cube root of x. And squared, I mean, we know that. Squared is just squared, right? So why is that so useful? What if I gave you, let's try it with an actual number. Let's try to simplify an expression using a number instead of a variable. What if we do something like, let's say, 16 to the 3/4? That looks complicated, but it's really simple.
Wait, would you do
How would you think of this?
1/4?
Exactly.
16 to the 4th cubed.
Exactly. You'd think of this as being 16
The 1/4.
to the 1/4 cubed. Exactly.
Wow.
And remember, what is,
Oh, I get it.
right? Okay, so what's another way of saying 16 to the 1/4?
16 to the 4th.
It's the 4th root. Yeah, that's the same thing as saying
2 to
a 4th root of 16 cubed, right?
Wow.
And so that's just, isn't that just equal to
plus or minus.
2? No, not plus or minus.
I thought it was.
No, because we're not solving an equation here, right? That x probably confused you, but we're just trying to evaluate just a root, right? So the 4th root of 16 is 2, cubed is 8, okay?
Got it.
That's it.
Who do we appreciate?
Not you.
Your teacher, of course.
Okay, so I don't know if this is like a silly question, but so there's a 16, so why don't you simplify that down if you're doing it to the 3rd? Like, how do you know it's just for the 1/4?
Okay, well, maybe this is what you're asking me. Could you do this as, maybe this is the question. You tell me if it is. Could I write this as 16 cubed to the 1/4? Well, I could, but 16 cubed is a huge number.
But it makes more sense to
Oh,
me.
yeah.
Well,
Yeah.
I meant like, you know how like you reduce the 3/4?
Mhm.
Why don't you reduce the 16? Is that just not?
You can't. You can't, because what the question is saying is this number to that power.
So you always keep like the x value or the 16 the same, and you just reduce what it's being.
Well, what you want to do if you can, yeah, what you want to do is you want to take, you want to break this up into a root and a power.
Okay.
It's a 4th root cubed.
Okay, so
Okay.
you never do anything to the root, you just do stuff to the power.
Yeah.
Okay.
Yeah, the base is being taken to those powers,
Okay.
right? Okay, so now you tell me this then. So what do you suppose, how am I going to write in terms of m's and n's and things like that? What if we want to rewrite a to the power of m divided by n? How am I going to write that as a radical?
Can't you just write it like that, but substitute the letters?
I can. So what's it going to look like?
N root of beta m.
Okay, the nth root of, whoops, not a, of a, of a
To the end.
to the m, sure. That's it, right?
Right.
No big deal. Okay, let's go maybe one step harder. Try this. Okay, what if I want, now try evaluating this. I want to know what is, what is 16 to the negative, don't say anything out loud, please. What is 16 to the negative 3/4? Now think about this. Who needs, get out your notebooks, if you need scratch paper, tell me. I'll throw some scratch paper at
It'll
you.
be negative, won't it?
Will you from this one?
I will. But throw it in.
No, it won't be
Throw it.
negative.
Okay.
It'll be a giant. That's
Okay.
how would we use
Oh, I know.
I'm kind of lost.
Do you want us just to like put it like this or keep going?
I'd like to know what the simplified answer is.
Got it.
What is it? 1/8. That's it. How'd you get it? Right here.
I got that.
Got it. Good.
I was on my way to that.
Okay. Shh. Right here. Listen.
Okay, you do the 4th root, or you separate it to do the 4th root, and then what? Negative cube root is 1/16 cubed.
Good. Okay, good. So we could write this as, everybody see this? We could write this as 16 to the 1/4 to the negative 3, right?
Wait, how is that one?
Okay.
Because you'd be because the negative cube root is flipped. It's 1/16.
Remember our property of exponents, a to the negative m, isn't that just 1 over a to the positive m?
Yeah.
Right? Okay, so 16 to the 1/4 is the same as what? A
4 squared to 6.
a 4th root of 16, right? Okay, so this is just going to be 2. Is that you guys? Oh my goodness. Okay, so 2 to the negative 3 is 1 over 2 to the positive 3,
Okay.
right? There you go. We made it. What's that? I not a ton. I mean, I can, depending on how quick I get the kids out the door.